Right, we need to understand the computed solutions of a spatial discretization. And one way to understand this is to look for equilibria and then look for the stability of those equilibria. In particular, linearise near the equilibria and find out the structure of solutions. So we're going to do that here using the coded functions that we've already done for the discretization. And so, for example, we'll look at the heat equation and we'll use the spatial discretization function for the time derivatives here exactly as we've coded it before, and we'll use the homogeneous boundary conditions, the zero boundary conditions, as used before, and we'll try and understand their behaviour by a numerical linearisation. Now, this numerical linearisation comes from eigenvalues and eigenvectors as derived by some linear algebra. Now, the challenge is that we do not know the matrix and hence we cannot find the eigenvalues and eigenvectors from the matrix. And the solution using MATLAB is to use the function eigs, and I can illustrate that in the following way. Right, let's try this very simple example of a matrix. 3 by 3 matrix of the numbers 1 to 9, like that. Now, normally if we're computing the eigenvalues and eigenvectors, we'd do something like this. V comma D is eig A. And because we've got the matrix A, we'd find out this information, that the eigenvalues are 0, minus 1.11, and 16.11. And the corresponding eigenvectors are above, in the column above those eigenvalues. Right, but here, when all we've got is the computer code of the function, we do not have the matrix. And this is where eigs comes in. Suppose we only know the product A times V, where we don't know A. So, for example, we might have coded the following function. Fun of a variable u, and what this function does internally is completely mysterious to us. Alright. Suppose we don't know what's going on inside that function, but we still want to know what its eigenvalues and eigenvectors are. Well, we do exactly the same sort of command, but we give the name of this function, and we use the function eigs. So we go eigs, name of the function, and then we say the size of the vectors involved. That's all it needs to know, that the vectors are three-dimensional vectors, and then we tell it the number of eigenvalues and eigenvectors we want. And for us, that'll always be the same as the size of the vector. And what do we find? Eigs goes away, does some internal machinations that derive the eigenvalues and eigenvectors exactly the same as eig does. So you can see down here the eigenvector 0, minus 1.11, 16.11 is the same as before, and the eigenvectors above are the same. Right, so eigs acting on a function tells us the information we need about the linearisation. So now let's use that for the diffusion partial differential equation that we've coded up here with its boundary conditions. Okay, how do we use eigs? Well, we take the simulation code that we have before and we started pretty much exactly the same. Right, set up some global variables, then specify the number of points in the domain, specify a grid over the domain, specify an index vector of the interior points on that grid, and then what we want is the equilibrium solution that we're going to linearise around. Now here for the diffusion equation we're going to linearise around the zero equilibrium. other examples we'll linearise about a non-trivial equilibrium. Okay, so the code is now, let's define a function that effectively computes A times V for a matrix A that we don't know. And we do it via numerical differentiation. So we define a small number. 10 to the minus 6 is usually appropriate, and this is because it's just a bit bigger than the square root of the machine precision. Right? The computer usually computes to 15 or 16 decimal places, so the smallest number compared to 1 that it can recognise is about 10 to the minus 15. Take the square root of that, it's about 10 to the minus 7. Choose a small number just a bit bigger than that, and that's usually what we want. Okay, so then we define a function which is the effective A times V, and what it is, it's just the time derivative function that we've already coded, evaluated at some arbitrary time, here 0, and then we want to know its value at the equilibrium plus a small amount of whatever it is eigs wants to know. Right, so this is a function of V, and we add to the equilibrium a small amount of V, whatever eigs chooses for V. And then we divide by small, and that's the A times V function. Okay, we then invoke eigs with the name of that function, fun, and because there's n points minus 2 interior points in the domain, then we say to eigs there are n points minus 2 variables in the vector, and we want all the eigenvalues and eigenvectors, so we ask for n points minus 2. And this will put the results of the eigenvectors in V and the eigenvalues in D, and one of the things we'll do is print out those eigenvalues by looking down what they are in the diagonal. So let's execute that code. Editor, run, change the folder, and here is the output that's popped up, and we'll get to the graph in a minute. The first thing is the eigenvalues. Here they are. And to compare with them are the analytic eigenvalues down here. And you should note two things. Firstly, they're different, that's because there's numerical approximations. But the small magnitude eigenvalues are pretty reasonable. So we've got 14 of them, and these roughly 1/3 of the smallest 1/3 are roughly good. So that would be these 5 coming from the numerics, and they correspond pretty well to the analytic ones, which are down here. And you might say they don't look the same, but remember there's a multiplication by 1,000 that has to apply to all of these numbers. Alright, so 1/3 are reasonable in the numerics. In the numerics, another third are sort of okayish, vaguely. And then the largest 1/3 in the numerics are really just rubbish. As you can see, these are varying from nearly 700 to 900, whereas the corresponding ones analytically vary from about 1,000 to 2,000. It's just off. So that's typical. 1/3 are good, 1/3 are okay-ish, and 1/3 are rubbish. So they're the eigenvalues. What about the eigenvectors? Well, that's what we've got plotted here. In this bottom window are the eigenvectors corresponding to the small eigenvalues, the smallest 5. And for example, the eigenvalue minus 9.83 corresponds to this shape, and you can see that looks pretty much like a sine pi x shape, which is the analytic solution. The minus 38.9 eigenvector, when plotted, is this shape, and that looks like sine 2 pi x, negative, and so on. These are all pretty reasonable sine waves. In the upper window, we've got plotted the eigenvectors of the largest eigenvalues, and you can see these are sawtooth modes, and they are not particularly accurate at all. And again, this is fairly typical. Whenever you see a numerical discretization of a PDE with such sawtooth structure, then your solution is inaccurate. Okay, so let's see, to draw these pictures, this is the sort of thing we can do. Firstly, as is commonly done in our graphics, we get the eigenvectors, and the eigenvectors are only the interior points, so we have to pad them out with the boundary values on either end, as we did for simulation, and that's that statement, and then we draw them. And this scenario of drawing two figures in the one is done using the subplot command. So we say subplot, we're going to have two rows of figures, one wide, and in the first one of the subplots we plot as a function of x the first four eigenvectors that are in V. And as it happens, those first four eigenvectors are the ones corresponding to the largest eigenvalues. We then label that plot with the eigenvalues by using the legend command and converting the eigenvalue values that are in D into strings for the legend command. And as usual, label the axes. Then to draw the bottom picture, again use the subplot command. So okay, we're drawing two graphs vertically, one horizontally, and we're now going to draw in the second one of those two. This command says plot the last 5 eigenvectors that are stored in V. And that's what we've drawn here. And then the legend command says to label those 5 curves, eigenvectors, by the corresponding eigenvalue that's found in D, using num to string. And that generates the legend there. And then the last thing is save that information to a file for including in reports, and remember that this is the way to save graphics and get the best quality result.